Right now, as you listen to these words, light from a distant monster is racing toward Earth. It left its source over 1 billion years ago. 1 billion years. That light began its journey before complex life even existed on our planet. It has been traveling through the emptiness of space at the fastest speed anything in the universe can move, for longer than you could ever truly understand. And when that ancient light finally reaches our telescopes, it shows us something that will break your sense of scale forever. There is a galaxy out there. It is sitting quietly in the darkness, more than 1 billion light years away from everything you have ever known. And it is so impossibly, incomprehensibly large that your mind will fight against accepting what I am about to tell you. This is not an exaggeration. This is not me being dramatic for effect. This is the simple truth about one of the most extreme objects ever discovered in the observable universe. The galaxy is called IC 1101, and by the time we are finished exploring it together, you will never look at the night sky the same way again. Let me be clear about something from the very beginning. You have probably heard impressive facts about space before. Maybe you learned that Jupiter is so big you could fit over 1,300 Earths inside it. That sounds huge, right? Jupiter is a giant compared to our little blue planet. Or perhaps someone told you that the sun is even more extreme, that you could pack roughly 1 million Earths into our star and still have room to spare. These numbers are meant to make you feel small. They are meant to give you some sense of the scale of our cosmic neighborhood. But here is what nobody prepared you for. All of those comparisons, every single one of them, become completely and utterly meaningless when you start talking about IC 1101. This galaxy is so far beyond anything in our everyday experience that the human brain simply was not built to handle it. We evolved on the plains of Africa, learning to judge distances to the next tree, the next watering hole, the next predator. Our minds are excellent at understanding things within a few miles. They start to struggle at distances of a few hundred miles, and they completely fall apart when we try to grasp millions, billions, or trillions of miles. So let me give you a number, and then I want you to really sit with it. IC 1101 contains an estimated 100 trillion stars. Let me write that out so you can see what it looks like. 100 trillion is 100,000, thousand, thousand, thousand. That is a 1 followed by 14 zeros. For comparison, our Milky Way galaxy, the vast cosmic city that contains our sun and every star you have ever seen in the night sky, holds somewhere between 200 billion and 400 billion stars. Even at the high estimate, IC 1101 has roughly 250 times more stars than our entire galaxy, but the star count is just the beginning. The size of this thing is where reality starts to feel like science fiction. IC 1101 stretches across space for somewhere between 4 million and 6 million light years. Now I know that number might not mean much to you yet, so let me break it down. A single light year is the distance that light travels in 1 year. Light moves at 186,000 miles per second. That is fast enough to circle the entire Earth more than 7 times in just 1 second. In 1 year, traveling at that unimaginable speed, light covers about 5.88 trillion miles, nearly 6 trillion miles in 12 months. Our Milky Way galaxy is about 100,000 light years across. That means if you could somehow travel at the speed of light, it would take you 100,000 years to cross from one side of our galaxy to the other. 100,000 years is longer than modern humans have existed as a species. It is longer than the entire history of human civilization, repeated over and over again. And that is just our galaxy. IC 1101 is roughly 40 to 60 times larger than the Milky Way. Take a moment with that. If you were a beam of light, the fastest thing in the entire universe, and you started at one edge of IC 1101 and tried to reach the other side, it would take you somewhere between 4 million and 6 million years to make that journey. Dinosaurs went extinct 66 million years ago. If light had started crossing IC 1101 when the dinosaurs were dying, it would have completed the trip and had plenty of time to spare before humans ever walked the Earth. And we are not talking about traveling somewhere. We are just talking about crossing a single galaxy. This is what I mean when I say your brain will struggle with this. The numbers are too big. The distances are too vast. Everything about IC 1101 exists on a scale that humans were never meant to comprehend. Here is another way to think about it. You know the Andromeda Galaxy? It is our nearest large galactic neighbor, a beautiful spiral of stars sitting about 2.5 million light-years away from us. The Milky Way and Andromeda are actually on a collision course. In about 4 to 5 billion years, our two galaxies will merge in a slow cosmic dance that will take millions of years to complete. When people imagine the far future of our galaxy, they often picture this merger as the most dramatic event imaginable. Two massive galaxies, each containing hundreds of billions of stars, are slowly combining into one. But here is the thing. If you took the Milky Way and Andromeda and combined them, the resulting merged galaxy would still be tiny compared to IC 1101. In fact, IC 1101 is so large that if it were placed where our Milky Way currently sits, it would swallow up not just Andromeda, but also the Triangulum Galaxy, the Large Magellanic Cloud, the Small Magellanic Cloud, and pretty much every other galaxy in what astronomers call the local group. Our entire neighborhood of galaxies, everything within about 10 million light-years of us, would fit comfortably inside this single cosmic giant. IC 1101 would eat our whole region of space for breakfast and barely notice. So where is this monster? How do we even know it exists? IC 1101 sits at the heart of something called the Abell 2029 galaxy cluster, located in the direction of the constellation Virgo, right near the border with the constellation Serpens. It is approximately 1.15 billion light-years from Earth. When astronomers point their telescopes at IC 1101, they are not seeing the galaxy as it exists right now. They are seeing it as it was 1.15 billion years ago, because that is how long the light has been traveling to reach us. When that light left IC 1101, life on Earth was still mostly single-celled organisms. Multicellular life was just beginning to experiment with new forms. The light we see today started its journey in an unimaginably ancient past. And what do we see when we look at this ancient light? We see a galaxy that has been described by scientists as possibly one of the largest and most luminous galaxies in the entire observable universe. IC 1101 is not just big in terms of size. It is classified as a supergiant elliptical galaxy, sitting at the absolute top of the galactic food chain. It is the brightest member of its entire galaxy cluster, earning it the designation of Brightest Cluster Galaxy, or BCG. In the Abell 2029 cluster, which contains thousands of galaxies, including hundreds of giants, IC 1101 outshines them all. One study found that it emits about 26% of all the light from the entire cluster, even though it is just one galaxy among thousands. But the story of IC 1101 is not just a story about size and brightness. It is a story about violence, consumption, and cosmic cannibalism on a scale that almost defies belief. Because IC 1101 did not start as the Titan we see today. No galaxy is born this large. IC 1101 became what it is through billions of years of mergers, collisions, and the ruthless absorption of smaller galaxies that wandered too close to its gravitational influence. Scientists believe that IC 1101 has devoured perhaps 10 or more major galaxies over its lifetime, along with countless smaller ones. The evidence for this cosmic feast is written into the very structure of the galaxy itself. IC 1101 has a strangely depleted core, a region at its center where you would expect to find dense concentrations of stars, but instead find relative emptiness. This happened because when galaxies merge, their central supermassive black holes spiral toward each other and eventually combine. During this process, they fling nearby stars outward like a cosmic slingshot, clearing out the core region. The fact that IC 1101's core shows such extreme depletion suggests a history of repeated major mergers. And speaking of black holes, IC 1101 contains one of the largest ever discovered. At its heart sits a supermassive black hole with an estimated mass of 40 to 100 billion times the mass of our Sun. Some studies suggest it could be even larger, perhaps approaching 100 billion solar masses. For comparison, the supermassive black hole at the center of our Milky Way, called Sagittarius A star, has a mass of only about 4 million solar masses. The black hole in IC 1101 is roughly 10,000 to 25,000 times more massive than ours. This is what we are dealing with. A galaxy so large that it could contain our entire cosmic neighborhood. A galaxy that has grown fat by consuming its neighbors over billions of years. A galaxy with a black hole at its center, so massive it would take thousands of copies of our own supermassive black hole to match it. A galaxy that has been shining its light across the universe for longer than complex life has existed on Earth. And somehow, through the power of human curiosity and the ingenuity of our telescopes, we have found it. We have measured it. We have come to understand it, at least in part. This is what makes astronomy such an incredible field. We are small creatures on a small planet, orbiting an ordinary star in an average spiral galaxy. And yet we have managed to peer across more than 1 billion light-years of space and discover something like IC 1101. We have taken the light that left that distant giant over 1 billion years ago and used it to calculate the galaxy's size, estimate its mass, count its stars, and probe its history. In the sections that follow, we are going to dive deep into everything we know about IC 1101. We will explore how galaxies are measured and why there is still some debate about the exact size of this cosmic titan. We will learn about the different types of galaxies that exist in the universe and why IC 1101 belongs to the most extreme category. We will examine the supermassive black hole at its center and understand how such an object can even exist. We will trace the violent history of mergers and collisions that built IC 1101 into what it is today. And we will look at what the future holds for this galaxy, because despite its size and power, IC 1101 is slowly dying. We will also talk about other galactic giants that have been discovered in recent years, including some that challenge IC 1101's claim to the throne in certain categories. The universe, as it turns out, is full of monsters, and the more we look, the more we find. But for now, I want you to carry this image with you as we continue. Somewhere out there, over 1 billion light-years away, sits a galaxy so large that light itself takes millions of years to cross it. It contains more stars than you could count in 1 million lifetimes. It has consumed entire galaxies the way a whale consumes plankton, and it has been there, quietly existing in the darkness, for billions upon billions of years. IC 1101. The biggest galaxy we have ever discovered. And I promise you, it is bigger than your imagination can handle. Before we dive deeper, I want to acknowledge something important. What we are about to explore together represents one of humanity's greatest intellectual achievements. For most of human history, people looked up at the night sky and saw only mystery. They created myths and legends to explain the stars, never imagining that those tiny points of light were other suns, many with their own planets, scattered across distances too vast to comprehend. They never dreamed that the faint smudge of light in the sky was actually another galaxy, let alone that there were trillions more beyond it. We are the first generation in the history of our species to truly know our place in the cosmos. We understand that we live in an unimaginably large universe, filled with structures so enormous they make our planet look like a grain of sand on an infinite beach. And among all those structures, IC 1101 stands as one of the most extreme examples of what the universe can create. That knowledge is precious. It connects us to something far larger than ourselves. Let us begin. Before we can truly understand what makes IC 1101 so extraordinary, we need to first understand our own place in the universe. We need to build a foundation, a sense of where we are, so that when we talk about a galaxy that could swallow entire galactic neighborhoods, you have something to compare it to. So let us start at home. You are sitting on a planet called Earth. It is a small, rocky world about 7,118 miles across at its widest point. If you could somehow drive a car around the entire equator at highway speeds without stopping, it would take you about 17 days. Earth feels big to us. It is the only world most humans will ever know. Every empire that ever rose and fell, every war ever fought, every love story ever told, all of it happened on this little ball of rock and water spinning through the void. But Earth is not alone. Our planet is just one of 8 major planets that orbit a star we call the Sun. Together, the Sun and all the objects that orbit it make up our solar system. And here is where our sense of scale starts to get challenged. The Sun is absolutely enormous compared to Earth. You could fit about 1.3 million Earths inside the Sun. If the Sun were a hollow ball, you could dump our entire planet inside it over 1 million times and still have room left over. The solar system itself stretches across billions of miles. Neptune, the outermost of the major planets, orbits the Sun at an average distance of about 2.8 billion miles. But even Neptune is not the edge of our solar system. Beyond it lies the Kuiper Belt, a region of icy objects and dwarf planets like Pluto. And beyond that, stretching perhaps 2 light-years from the Sun, is the Oort cloud, a vast spherical shell of comets and frozen debris that marks the true outer boundary of our star's gravitational influence. All of this, everything from Mercury to the most distant icy rock in the Oort cloud, is our cosmic neighborhood. It is our address within the galaxy. And yet, as vast as our solar system seems, it is almost nothing compared to the galaxy that contains it. The Milky Way is our home galaxy. It is a barred spiral galaxy, which means it has a distinctive shape that astronomers have spent centuries trying to understand. Picture a giant pinwheel of stars, gas, and dust slowly rotating through space. At its center sits a dense bulge of older stars, roughly 10,000 light-years across. Running through this central bulge is a bar-shaped structure made of millions of stars, and extending outward from the ends of this bar are the great spiral arms that give our galaxy its characteristic appearance. Now, let me give you some numbers that will help you understand the scale we are dealing with. The Milky Way is approximately 100,000 light-years across. I mentioned light-years in the introduction, but let me break this down more carefully, because understanding what a light-year actually means is essential to grasping the rest of our story. Light is the fastest thing in the universe. Nothing can travel faster than light. It moves at exactly 299,792 kilometers per second, or about 186,000 miles per second. At that speed, light could circle the entire Earth more than 7 times in a single second. It could travel from New York to Los Angeles in about 1/60th of a second. Light is unimaginably fast. And yet, even at that incredible speed, light still takes time to cross vast distances. It takes about 8 minutes for light from the sun to reach Earth. That means when you look at the sun, assuming you do not damage your eyes in the process, you are seeing it as it was 8 minutes ago. If the sun suddenly vanished right now, we would not know about it for 8 minutes. A light year is the distance that light travels in 1 year. Over the course of 12 months, moving at 186,000 miles per second without stopping, light covers about 5.8 trillion miles, nearly 6 trillion miles in a single year. That number is already incomprehensible to the human mind. Our brains simply did not evolve to handle distances measured in trillions of miles. So when I tell you that the Milky Way is 100,000 light years across, I need you to understand what that means. If you could somehow travel at the speed of light, the absolute maximum velocity allowed by the laws of physics, it would take you 100,000 years to cross from one side of our galaxy to the other. 100,000 years. That is longer than modern humans have existed as a species. Homo sapiens first appeared roughly 300,000 years ago, but we only developed agriculture about 10,000 years ago. Everything we call civilization, everything from the first cities to the smartphone in your pocket, happened in the last 10,000 years. And yet 100,000 years would not even be enough time to cross our own galaxy at the speed of light. The Milky Way contains somewhere between 200 billion and 400 billion stars. The exact number is uncertain because counting stars in a galaxy is extraordinarily difficult, especially when you are inside that galaxy looking out. But even at the low estimate of 200 billion, the number is staggering. If you tried to count every star in the Milky Way, counting one star per second without sleeping or eating or doing anything else, it would take you over 6,300 years to finish. Our sun is just one of those hundreds of billions of stars. It sits about 26,000 light years from the galactic center, in a region called the Orion Arm. The Orion Arm is a minor spiral arm, sometimes called a spur, located between two larger arms known as the Perseus Arm and the Sagittarius Arm. We are not at the center of anything. We are in the suburbs, roughly halfway between the galactic core and the outer edge of the disk. From our position in the Orion Arm, we cannot see the center of the Milky Way with our naked eyes. There is too much dust and gas in the way. But we can see the glow of billions of distant stars when we look along the plane of the galaxy. That is what creates the milky band of light that stretches across our night sky. The feature that gave our galaxy its name. Here is something that might blow your mind. Even though the Milky Way is enormous beyond comprehension, the sun is actually moving through it at tremendous speed. Our entire solar system is orbiting the center of the galaxy at approximately 515,000 miles per hour. That is over 200 kilometers per second. At that speed, you could travel from Earth to the Moon in about half an hour. But even at 515,000 miles per hour, the Milky Way is so large that it takes the sun approximately 225 to 250 million years to complete a single orbit around the galactic center. Astronomers call this period a cosmic year or a galactic year. In the entire 4.5 billion year history of our solar system, the sun has completed only about 18 to 20 orbits around the galaxy. Think about what the Earth was like the last time we were in this position in our galactic orbit. 225 million years ago, the dinosaurs had not yet evolved. The supercontinent Pangaea was just beginning to break apart. Life was recovering from the largest mass extinction in Earth's history, the Permian-Triassic extinction event that killed roughly 90% of all species on the planet. That is how long one trip around the galaxy takes. Now, here is another concept that helps illustrate the true emptiness of space. Our nearest stellar neighbor is a star called Proxima Centauri, part of the Alpha Centauri system. Proxima Centauri is about 4.24 light-years away. That makes it close by galactic standards, practically next door. And yet, that distance of 4.24 light-years translates to roughly 25 trillion miles. If you wanted to visualize how space really is, try this thought experiment. Shrink the sun down to the size of a grain of sand, about 1 millimeter across. At that scale, Proxima Centauri would be another grain of sand located about 4 miles away. Between those two grains of sand, there would be nothing but space. No planets, no asteroids, no comets. Just 4 miles of absolute emptiness between two specks of sand. That is how spread out the stars are in our galaxy. Even though the Milky Way contains hundreds of billions of stars, space is so vast that each star has an enormous amount of room around it. Collisions between stars are rare. The distances involved are simply too great. The space between stars is not empty, though. There is gas and dust scattered throughout the galaxy, concentrated mostly in the spiral arms. This gas is mostly hydrogen, the simplest and most abundant element in the universe. When gravity pulls this gas together into dense clouds, new stars are born. The Milky Way is still actively forming stars today, mostly in the spiral arms where the gas is densest. Our sun was born in one of these stellar nurseries about 4.6 billion years ago. And speaking of the Milky Way, its name has a beautiful origin story that reflects how ancient peoples tried to understand what they were seeing. The ancient Greeks looked up at that hazy band of light stretching across the sky and wove a myth to explain it. According to their legend, the goddess Hera was tricked into nursing the infant Heracles, the son of her unfaithful husband, Zeus, and a mortal woman. When Hera discovered what was happening and pushed the baby away, her divine milk sprayed across the heavens, creating the milky streak we see today. The Greek name for this band of light was Galaxias, derived from their word for milk, Gala. That is where we get the word galaxy. Different cultures saw different things in that milky band of stars. The Romans, influenced by Greek culture, called it Via Lactea, the Milky Road, and their poets imagined it as the path the gods traveled to reach the palace of Jupiter on Mount Olympus. The Roman writer Ovid described it as a shining road through the heavens, a celestial highway of unimaginable splendor. In Chinese tradition, the Milky Way was known as the Silver River, or Yinhe, and it played a central role in one of the most beloved stories in Asian culture, the legend of the Weaver Girl and the Cowherd. According to the tale, Xinu, the Weaver Girl represented by the star Vega, fell in love with Niulong, the Cowherd represented by the star Altair. Their love so distracted them from their duties that the gods separated them by creating the Silver River between them. Now they can only meet once a year, on the 7th day of the 7th lunar month, when a flock of magpies forms a bridge across the celestial river. This festival is still celebrated today in China, Japan, Korea, and Vietnam. The Norse peoples of Scandinavia had their own interpretation. They saw the Milky Way as the road to Valhalla, the great hall where warriors who died bravely in battle were welcomed by Odin. For the Lakota people of North America, the Milky Way was the spirit road, the path that souls traveled after death to reach the afterlife. The Cherokee told a story of a dog that stole cornmeal and ran away across the sky, spilling the meal as it fled, creating the glowing band we see today. Aboriginal Australian peoples, who developed sophisticated astronomical knowledge over tens of thousands of years, saw the Milky Way in various ways, depending on the group. The Kaurna people of the Adelaide Plains called it Wadlaperi, meaning river, and believed campfires were scattered along its length. The Yolngu people of Arnhem Land saw it as a river of fish. In the Kimberley region of Western Australia, Aboriginal peoples called the Milky Way Iowara, and saw in it the shape of a giant emu stretched across the sky. Remarkably, they focused not on the bright stars, but on the dark patches of dust that block the light behind them, seeing the emu's shape in the darkness between stars. The San people of southern Africa told a story about a lonely girl who threw embers from a fire into the sky to create light so she could find her way to visit other people. Those embers became the stars of the Milky Way. In Hindu tradition, the galaxy was called Akash Ganga, the Ganges river of the sky, a celestial reflection of the sacred river that flows through India. These myths share remarkable similarities, despite coming from cultures separated by oceans and millennia. People across the world looked up and saw rivers, roads, and pathways. They saw journeys and stories of love, loss, and transformation. The Milky Way has always sparked the human imagination, inspiring us to create meaning from the lights in the darkness above our heads. For most of human history, people had no idea what the Milky Way actually was. They did not know it was made of stars. They did not know it was a galaxy. They did not even have the concept of a galaxy. The Milky Way was simply a mystery, a glowing band of light in the night sky that inspired myths and legends across every culture that gazed upon it. It was not until Galileo Galilei pointed his crude telescope at the Milky Way in 1610 that humans began to understand its true nature. Through his lens, Galileo saw that the milky glow was not a continuous band of light at all. It was composed of countless individual stars, too faint and too numerous to distinguish with the naked eye. This was a revolutionary discovery. It meant the universe was far larger and more populated than anyone had imagined. But even Galileo had no idea just how large the Milky Way was, or that it was merely one galaxy among trillions. That understanding would take centuries more to develop, and it would require telescopes far more powerful than anything Galileo could have dreamed of. This is our cosmic address. We live on a small rocky planet orbiting an average star in the suburbs of a barred spiral galaxy containing hundreds of billions of stars, a galaxy so vast that light itself takes 100,000 years to cross it, a galaxy where our solar system completes one orbit every 225 million years. This is where we are. And compared to IC 1101, the Milky Way is practically a cosmic speck. The story of how we discovered IC 1101 is really the story of how we discovered galaxies at all. For most of human history, we did not even know that other galaxies existed. The very idea that there could be other vast collections of stars beyond our own Milky Way was not just unknown, it was almost unthinkable. The revolution in understanding that led us to IC 1101 is one of the greatest intellectual journeys in the history of science. Let us go back to where it all started. After Galileo showed that the Milky Way was made of stars in 1610, astronomers spent the next few centuries cataloging the heavens with increasingly powerful telescopes. They mapped stars, tracked comets, observed planets, and tried to understand the structure of the universe. But one thing kept puzzling them. Scattered across the sky were faint, fuzzy patches of light that did not look like stars. They were not points of light. They were smeared, cloudy, nebulous. Astronomers called them nebulae, from the Latin word for cloud. Some of these nebulae turned out to be exactly what they appeared to be: clouds of gas and dust within our own galaxy. The Orion Nebula, visible to the naked eye as a fuzzy star in Orion's sword, is a stellar nursery where new stars are being born right now. But other nebulae looked different. Some of them had a distinctive spiral shape, like cosmic pinwheels slowly turning in the depths of space. These spiral nebulae posed a question that would take centuries to answer. What were they? One of the most prolific observers of nebulae was a German-born British astronomer named William Herschel. Herschel was a musician who became obsessed with astronomy and taught himself to build some of the finest telescopes in the world. Using these instruments from his observatory in Slough, England, he systematically surveyed the night sky, discovering thousands of new objects, including nebulae, star clusters, and even the planet Uranus. On June 19, 1790, Herschel pointed his telescope at a faint smudge of light in the direction of the constellation Virgo, near the border with Serpens. He recorded it as a nebulous feature, a faint round patch with a gradually brighter center. He had no idea what he was looking at. He certainly had no idea that this faint smudge was actually the largest galaxy ever discovered, visible from over 1 billion light-years away. It was just another entry in his catalog, another mystery in the sky waiting to be solved. The object that Herschel observed would eventually be designated IC 1101, but that name would not come for over a century. In the meantime, Herschel and his son John continued their surveys, cataloging thousands of nebulae and star clusters. John Herschel took his father's telescopes to South Africa to survey the southern sky, and eventually published the General Catalogue of Nebulae and Clusters of Stars in 1864, containing over 5,000 objects. In 1888, a Danish-Irish astronomer named John Louis Emil Dreyer compiled an even more comprehensive catalogue. His new General Catalogue of Nebulae and Clusters of Stars contained 7,140 objects, and the NGC numbers he assigned are still used by astronomers today. Objects like NGC 224, better known as the Andromeda Galaxy, carry Dreyer's designations. But Dreyer was not done. As photography began to revolutionize astronomy in the late 1800s, observers were discovering new nebulae faster than ever before. In 1895 and 1908, Dreyer published 2 supplements to his catalog called the Index Catalogues. The first Index Catalog, published in 1895, contained 1,520 objects discovered between 1888 and 1894. Among them was the object Herschel had observed on that June night in 1790. Dreyer assigned it the designation IC 1101, the 1,101st object in the Index Catalog. The name is somewhat arbitrary. IC 1101 simply means it was the 1,101st object added to that particular catalog. It says nothing about the object's size, distance, or significance. But that simple designation would eventually become famous as the name of the largest known galaxy in the universe. Throughout the late 1800s and early 1900s, astronomers fiercely debated the nature of the spiral nebulae. Were they relatively small gas clouds within our own Milky Way? Or were they something far grander, entire galaxies in their own right, separated from us by vast distances? The stakes of this debate were enormous. If the spiral nebulae were just clouds of gas in our galaxy, then the Milky Way might be the entire universe. But if they were separate galaxies, the universe would be almost unimaginably larger than anyone had thought. This controversy came to a head in what is now known as the Great Debate, held on April 26, 1920, at the Smithsonian's National Museum of Natural History in Washington, D.C. The two combatants were Harlow Shapley and Heber Curtis, both respected astronomers with very different views on the nature of the universe. Shapley was a young, ambitious astronomer who had made his name studying globular clusters, the ancient spherical collections of stars that orbit the Milky Way. Using a type of pulsating star called Cepheid variables, Shapley had calculated that the Milky Way was far larger than anyone had previously believed. He argued that our galaxy was about 300,000 light-years across, 10 times larger than most estimates. If the Milky Way was that enormous, Shapley reasoned, then the spiral nebulae were probably just small objects within it. The Milky Way, in his view, was essentially the entire universe. Curtis held the opposite view. He believed the Milky Way was much smaller than Shapley claimed, perhaps only 30,000 light-years across. More importantly, Curtis was convinced that the spiral nebulae were not objects within our galaxy at all. They were island universes, separate galaxies each containing billions of stars, located at enormous distances from the Milky Way. If Curtis was right, the universe was filled with countless galaxies stretching out to distances beyond imagination. The Great Debate of 1920 did not produce a clear winner. Both astronomers presented their evidence, argued their cases, and came away unconvinced by the other's position. The data available at the time was simply not good enough to settle the question definitively. But the debate captured the imagination of the scientific community and the public. Everyone wanted to know the answer. Was the Milky Way everything? Or was it just one galaxy among many? The answer came just a few years later, from a young astronomer named Edwin Hubble working at Mount Wilson Observatory in California. Hubble had access to the most powerful telescope in the world at that time, the 100-inch Hooker telescope, and he was using it to study the spiral nebulae in unprecedented detail. In October 1923, Hubble was examining photographic plates of the Andromeda Nebula when he discovered something remarkable. He had found what he initially thought was a nova, a type of exploding star. But as he continued to observe it over the following nights, he realized this was no ordinary nova. The star was brightening and dimming in a regular pattern. Hubble recognized it as a Cepheid variable. This was the key to everything. Cepheid variable stars are cosmic lighthouses. They pulsate with a very specific rhythm, brightening and dimming over periods ranging from a few days to a few weeks. And here is the crucial thing. The period of a Cepheid's pulsation is directly related to its intrinsic brightness. A Cepheid that takes longer to complete one cycle is brighter than one that pulsates quickly. This relationship was discovered by Henrietta Swan Leavitt, an astronomer at Harvard, in 1912. Because astronomers knew the intrinsic brightness of Cepheids based on their periods, they could compare that to how bright the star appeared from Earth and calculate its distance. The fainter it appeared compared to what it should be, the farther away it must be. Cepheids were cosmic yardsticks, allowing astronomers to measure distances across the universe. Hubble measured the period of the Cepheid he had found in Andromeda. It was about 31 days. From that period, he calculated the star's intrinsic brightness. Then he compared that to how faint it appeared in his photographs. The result was stunning. The Andromeda Nebula was not a cloud of gas inside our galaxy. It was at least 900,000 light-years away, far beyond the most generous estimates of the Milky Way's size. Andromeda was a separate galaxy, an island universe containing billions of its own stars, utterly independent of our Milky Way. Hubble wrote a letter to Harlow Shapley sharing his discovery. When Shapley read it, he reportedly said to a colleague, Here is the letter that destroyed my universe. In a single discovery, Hubble had expanded the known universe by an almost unimaginable factor. The Milky Way was not everything. It was just one galaxy among what we now know are at least 2 trillion galaxies in the observable universe. By the end of 1924, Hubble had found 36 variable stars in Andromeda, including 12 Cepheids. Using all of them, he calculated a distance of about 900,000 light-years. Modern measurements, using better data and accounting for different types of Cepheids, put Andromeda at about 2.5 million light-years away. Hubble's initial estimate was off by a factor of about 3, but he had gotten the essential point right. Andromeda was far, far outside our galaxy. The implications were revolutionary. Every spiral nebula that astronomers had been arguing about was suddenly transformed into a galaxy. Those faint smudges of light scattered across the sky were not local phenomena. They were entire stellar cities, each containing hundreds of billions of stars, each separated from us by distances measured in millions of light-years. The universe had just become almost incomprehensibly larger. Over the following years and decades, astronomers continued to push outward, measuring distances to more and more galaxies. They discovered that the universe was not static, but expanding, with galaxies flying away from each other as space itself stretched. They learned that the light from distant galaxies was shifted toward the red end of the spectrum, evidence of this cosmic expansion. They realized that looking at distant galaxies was like looking back in time, seeing the universe as it existed billions of years ago. Hubble himself continued to be at the forefront of these discoveries. In 1929, he published perhaps his most famous finding, the relationship between a galaxy's distance and how fast it appears to be moving away from us. Galaxies twice as far away are moving away twice as fast. This relationship, now called Hubble's law, provided the first observational evidence that the universe is expanding. If you run the expansion backward in time, everything converges to a single point, a moment when all matter and energy were compressed into an infinitely small, infinitely dense state. This was the first observational hint of what we now call the Big Bang. The implications were profound. The universe was not eternal and unchanging. It had a beginning. It was evolving. And it was far, far larger than anyone had imagined. Astronomers estimated that there were millions of galaxies in the observable universe. Then they revised that to billions. Today, using the most sensitive telescopes ever built, we estimate that there are at least 2 trillion galaxies in the observable universe. 2 trillion island universes, each containing billions or hundreds of billions of stars. And in all of this exploration, IC 1101 was waiting. That faint smudge that William Herschel had observed in 1790, the object that Dreyer had catalogued in 1895, was still there, still broadcasting its ancient light across the cosmos. But it would take the development of more sophisticated techniques and more powerful telescopes before astronomers could truly understand what they were looking at. By the mid-20th century, astronomers had developed new tools for measuring distances to extremely remote galaxies. They used the brightness of entire galaxies as distance indicators. They studied the redshift of galactic spectra to determine how fast the universe was carrying these objects away from us, and from that inferred their distances. They learned to identify different types of supernovae, stellar explosions of known brightness that could serve as cosmic distance markers reaching even farther than Cepheid variables. In the 1960s and 1970s, astronomers began systematically studying galaxy clusters, and they became particularly interested in the giant galaxies that sat at the centers of these clusters. They noticed that these central galaxies were special. They were almost always the brightest and most massive members of their clusters. They often had extended halos of stars that seemed to merge with the diffuse light between galaxies, and some of them, like IC 1101, were absolutely enormous. When they finally did measure the distance to IC 1101, they found something remarkable. The galaxy was not millions of light years away like Andromeda. It was over 1 billion light years away. The light that had triggered Herschel's eye in 1790 had left IC 1101 over 1 billion years before it reached his telescope. He had been looking at light that was old when dinosaurs still walked the Earth, and the size of this distant object was even more staggering. IC 1101 was not just another galaxy. It was the largest galaxy anyone had ever found, a cosmic giant that made even our impressive Milky Way look like a dwarf. The journey from thinking the Milky Way was everything to discovering IC 1101 represents one of the greatest expansions of human knowledge in history. In just over a century, we went from not knowing galaxies existed to finding one so large it defies comprehension. That is the power of science. That is what human curiosity, combined with technology and persistence, can achieve. We started with a faint smudge in an eyepiece and ended up measuring a structure millions of light years across, sitting at the heart of a vast galaxy cluster over 1 billion light years away. Not bad for a species that only invented the telescope about 400 years ago. Now that we understand how galaxies were discovered, we need to talk about the incredible diversity of galaxies that fill our universe. Not all galaxies are created equal. They come in a stunning variety of shapes and sizes, from tiny dwarf galaxies containing just a few billion stars to monstrous giants containing trillions. Understanding this diversity is essential to appreciating just how extreme IC 1101 really is. After Edwin Hubble proved that galaxies existed, he set about trying to classify them. Hubble was a meticulous observer, and as he studied galaxy after galaxy through the 100-inch telescope at Mount Wilson, he noticed that they seemed to fall into distinct categories based on their appearance. In 1926, he published his classification scheme, which astronomers still use today. It is called the Hubble sequence, and it is often depicted as a diagram that looks like a tuning fork. On the left side of the tuning fork are the elliptical galaxies. These are the simplest looking galaxies, appearing as smooth, featureless blobs of light. They range from nearly spherical to highly elongated, shaped like footballs or cigars. Hubble classified them with the letter E, followed by a number indicating how elongated they appeared. E0 galaxies look almost perfectly round, while E7 galaxies are highly stretched out. The number is calculated from the ratio of the galaxy's longest axis to its shortest axis. Elliptical galaxies are dominated by old red stars. They have very little gas and dust, which means they are not actively forming new stars. When you look at an elliptical galaxy, you are seeing a stellar population that formed billions of years ago and has been slowly aging ever since. These are the retirement homes of the galaxy universe, places where star formation has essentially stopped. The sizes of elliptical galaxies vary enormously. At the small end are dwarf elliptical galaxies, some containing only a few million stars. These tiny systems are actually the most common type of galaxy in the universe, but they are so faint that they are hard to detect except in our local neighborhood. At the large end are giant and supergiant elliptical galaxies, some of which are the largest galaxies known. IC 1101 falls into this category. Moving along the handle of the tuning fork, we come to a transitional class called lenticular galaxies, designated S0. Lenticular galaxies have a disk-like structure similar to spiral galaxies, but they lack the distinctive spiral arms. They have a central bulge of stars surrounded by a flattened disk, but the disk appears smooth and featureless. Think of them as spiral galaxies that have used up their gas and stopped forming stars, or as elliptical galaxies that happen to have a disk. Astronomers are still debating exactly how lenticular galaxies form, but they seem to represent an intermediate stage between spirals and ellipticals. At the point where the tuning fork splits into two prongs, we find the spiral galaxies. These are the classic pinwheel-shaped galaxies, with beautiful spiral arms winding outward from a central bulge. The Milky Way is a spiral galaxy, as is our neighbor Andromeda. Spiral galaxies are divided into two branches on the tuning fork: normal spirals and barred spirals. Normal spirals, designated with the letter S, have arms that appear to emerge directly from the central bulge. Barred spirals, designated SB, have a distinct bar of stars running through the center, with the spiral arms beginning at the ends of this bar. The Milky Way is actually a barred spiral, though we did not realize this until relatively recently. Both types of spirals are further subdivided into categories A, B, and C, based on how tightly wound their arms are and how large their central bulges are. SA and SBA galaxies have large bulges and tightly wound arms. SC and SBC galaxies have small bulges and loosely wound arms that are often rich in young blue stars and glowing nebulae. SB and SBB galaxies fall in between. Spiral galaxies are active, dynamic places. Their arms are regions of enhanced density, where gas compresses and triggers star formation. When you look at a spiral galaxy, you see both old red stars in the bulge and young blue stars in the arms. You see the glow of nebulae where new stars are being born. Spiral galaxies are still building new generations of stars, unlike the elderly ellipticals. Finally, there is a fourth category that does not quite fit the tuning fork: irregular galaxies. These are galaxies that do not have any clear symmetrical structure. They are often chaotic, disturbed, or oddly shaped. Some irregular galaxies are in the process of merging with other galaxies, their structures torn apart by gravitational forces. Others are small, gas-rich systems that never developed clear spiral arms. The Large and Small Magellanic Clouds, two small galaxies that orbit the Milky Way, were originally classified as irregular galaxies, though astronomers later found evidence of weak spiral structure in the Large Magellanic Cloud. Now, the Hubble classification tells us about a galaxy's shape, but it does not tell us about its size. And size matters enormously when you are talking about galaxies. At the small end of the spectrum are dwarf galaxies. These are galaxies containing anywhere from a few million to a few billion stars. That might sound like a lot, but remember that the Milky Way has somewhere between 200 and 400 billion stars. A typical dwarf galaxy is 100 times smaller than our galaxy. Dwarf galaxies are actually the most numerous type of galaxy in the universe, but because they are so faint, we can only see them if they are relatively close to us. The Large and Small Magellanic Clouds are two of the best-known dwarf galaxies. Visible from the southern hemisphere as fuzzy patches of light that look like detached pieces of the Milky Way, they have been known to humans for thousands of years. Aboriginal Australians and Polynesian navigators observed them long before European explorers named them after the Portuguese explorer Ferdinand Magellan, who documented them during his voyage around the world in 1519 to 1522. The Large Magellanic Cloud is about 160,000 light-years from Earth and contains roughly 20 billion stars. That makes it a substantial galaxy by dwarf standards, but still 100 times smaller than the Milky Way in terms of stellar mass. The Large Magellanic Cloud is particularly interesting because it is visibly irregular, with a bar structure and hints of spiral arms that have been distorted by gravitational interactions with our galaxy. It is also home to the Tarantula Nebula, one of the most active star-forming regions known, where new stars are being born at a prodigious rate. The Small Magellanic Cloud is even smaller, containing only about 3 billion stars and located about 200,000 light-years away. Both Magellanic Clouds are connected to the Milky Way by streams of hydrogen gas called the Magellanic Stream, evidence that our galaxy has been gravitationally interacting with these smaller companions for hundreds of millions of years. The Milky Way has numerous other dwarf galaxy satellites orbiting it. The Sagittarius Dwarf Elliptical Galaxy is slowly being torn apart by our galaxy's gravity, its stars streaming out in long tidal tails that wrap around the Milky Way. The Canis Major Dwarf Galaxy is even closer, located only about 25,000 light-years from Earth, though some astronomers debate whether it is actually a separate galaxy or just a feature of the Milky Way's structure. These tiny systems are being gradually absorbed by the Milky Way, adding their stars to our galactic population. In a sense, our galaxy is a cannibal too, consuming smaller companions over cosmic time. The smallest dwarf galaxies are almost unbelievably faint. Ultra-faint dwarf galaxies contain only a few thousand stars and are dominated by dark matter. Some of these systems have dark matter halos that are hundreds of times more massive than their visible stars. Finding these objects is extremely challenging because their combined light output is less than that of a single bright star. At the other end of the spectrum are the giant and supergiant galaxies. These are the titans of the universe, galaxies containing trillions of stars and stretching across hundreds of thousands or even millions of light years. And here is where our story starts to connect back to IC 1101. The largest galaxies in the universe are almost always found in a specific location, the centers of galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds or even thousands of galaxies, all held together by their mutual gravity. The mass of a typical galaxy cluster is about 1,000,000 billion times the mass of the Sun, though most of that mass is actually dark matter. At the center of almost every galaxy cluster sits a special galaxy called the Brightest Cluster Galaxy, or BCG. As the name suggests, BCGs are the most luminous galaxies in their clusters. They are also typically the most massive, and they did not get that way by accident. BCGs grow through a process astronomers call galactic cannibalism. Over billions of years, these central galaxies consume smaller galaxies that wander too close. The smaller galaxy falls into the gravitational pull of the BCG, gets torn apart by tidal forces, and has its stars absorbed into the larger galaxy. Through repeated mergers, BCGs can grow to enormous sizes. A special subtype of BCG is the CD galaxy. The classification comes from an old system where C indicated supergiant size and D referred to a particular surface brightness profile. CD galaxies are distinguished by their enormous extended halos. A typical CD galaxy has a central region that looks like a giant elliptical galaxy, surrounded by a vast, diffuse envelope of stars that can stretch for hundreds of thousands of light years beyond the main body. These extended halos are thought to be made of stars that were stripped from smaller galaxies during mergers. They form a kind of stellar fog surrounding the central galaxy, a population of orphaned stars that no longer belong to any particular system. In some CD galaxies, the halo is so extended that it becomes difficult to define where the galaxy ends and the surrounding intergalactic space begins. IC 1101 is a CD galaxy. It is the brightest galaxy in its cluster, Abell 2029. It has grown enormous through billions of years of consuming smaller galaxies, and its extended halo stretches out to distances that are almost hard to believe. There is one more concept we need to understand before we dive into IC 1101 itself, and that is the relationship between a galaxy's mass and the mass of the black hole at its center. Almost every large galaxy has a supermassive black hole at its center. The Milky Way has one called Sagittarius A star, with a mass of about 4 million times the mass of the Sun. Andromeda's central black hole is about 100 million solar masses. These black holes are called supermassive because ordinary stellar black holes, which form when massive stars die, are typically only a few times the mass of the Sun. Supermassive black holes are millions or billions of times heavier. Here is the remarkable thing. There is a tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. Bigger galaxies tend to have bigger black holes. This relationship holds across an enormous range of galaxy sizes, suggesting that the growth of galaxies and the growth of their central black holes are intimately connected. When a galaxy consumes another galaxy, the two central black holes eventually spiral together and merge, creating an even larger black hole. This means that if IC 1101 is the largest galaxy we know, it probably has one of the largest black holes we know as well. And as we will see, this prediction is spectacularly confirmed by observations. The Abell catalog, published by astronomer George Abell in 1958, contains 2,712 galaxy clusters visible from the northern hemisphere. A later supplement added clusters visible from the south. These clusters range from modest collections of a few dozen galaxies to enormous structures containing thousands of members. Abell 2029, the home of IC 1101, is one of the more massive clusters in the catalog, a dense concentration of galaxies held together by an enormous halo of dark matter. Understanding all of this context, all of these different types and sizes of galaxies, all of these processes of merging and growth, prepares us for what comes next. Because IC 1101 is not just a big galaxy, it is not just a BCG, it is not just a CD galaxy with an extended halo. It is all of these things pushed to their absolute extreme. It is the king of galaxies, the result of billions of years of cosmic growth and consumption, the largest single stellar system we have ever discovered, and now we are finally ready to meet it properly. We have built up our understanding step by step. We know where we are in the universe. We know how galaxies were discovered. We know the different types and how they grow. Now it is time to turn our full attention to IC 1101, the supergiant elliptical galaxy that sits like a cosmic emperor at the heart of Abell 2029. Let us start with the basics of where IC 1101 is located. The galaxy sits at the center of the Abell 2029 galaxy cluster in the direction of the constellation Virgo, right near the border with the constellation Serpens. When astronomers point their telescopes at coordinates right ascension 15 hours, 10 minutes, 56 seconds, declination plus 5 degrees, 44 minutes, 41 seconds, they are looking at IC 1101. The distance to IC 1101 is approximately 1.15 billion light years. Let that number sink in for a moment. When you look at light from IC 1101, you are not seeing the galaxy as it exists today. You are seeing it as it existed 1.15 billion years ago. The photons hitting our telescopes left IC 1101 when life on Earth was still mostly single-celled organisms. The Cambrian explosion, when complex multicellular life first flourished, was still hundreds of millions of years in the future. The light we see today is profoundly ancient. At that distance, measuring the size of IC 1101 becomes complicated. Astronomers use several different methods to measure galaxy sizes, and they do not always agree with each other. This is why you might see different numbers quoted for IC 1101's diameter, depending on which source you consult. Understanding why these measurements differ helps us appreciate both the challenges of studying distant objects and the true scale of this cosmic giant. The most commonly cited measurement is called the isophotal diameter. This is the diameter measured out to a specific brightness level, a contour where the galaxy fades to a particular surface, brightness against the darkness of space. Different studies use different brightness thresholds, which leads to different size measurements. The D25 isophotal diameter, which measures out to a surface brightness of 25 magnitudes per square arcsecond in the B band, blue light, is one standard measurement. Using this method, IC 1101 has a diameter somewhere between 400,000 and 550,000 light-years. Even at the low end of that range, IC 1101 would be 4 times the diameter of the Milky Way. At the high end, it would be more than 5 times larger. Some measurements in the K-band, near-infrared light, which penetrates dust better and traces older stellar populations more accurately, give slightly different values. Infrared observations are particularly useful for studying elliptical galaxies like IC 1101 because they are less affected by dust extinction and trace the bulk of the stellar mass. But here is where IC 1101 gets truly mind-bending. The isophotal diameter only measures the bright core of the galaxy. IC 1101, as a CD galaxy, has an enormous extended halo of stars that stretches far beyond this central region. When astronomers use deep imaging techniques that can detect extremely faint light, they find that IC 1101's stellar halo continues outward to astonishing distances. Some measurements suggest that this diffuse envelope extends to a radius of more than 1 megaparsec from the galaxy's center. When astronomers include this diffuse envelope, the total diameter of IC 1101 may reach 4 to 6 million light-years. 6 million light-years. Let me put that in perspective. The distance from the Milky Way to the Andromeda Galaxy is about 2.5 million light-years. If IC 1101 were centered where our galaxy sits right now, with its full extended halo, it would stretch out past the Andromeda Galaxy. Andromeda would be inside IC 1101. In fact, the entire local group of galaxies, the collection of over 80 galaxies that includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of dwarf galaxies scattered across a region about 10 million light-years across, would fit inside IC 1101 with room to spare. One galaxy, containing the equivalent of our entire galactic neighborhood. The star count in IC 1101 is equally staggering. Astronomers estimate that IC 1101 contains roughly 100 trillion stars. That is 100,000 stars. For comparison, the Milky Way has perhaps 200 to 400 billion stars. Even the Andromeda Galaxy, which is larger than our galaxy, has only about 1 trillion stars. IC 1101 has roughly 100 times more stars than Andromeda, and perhaps 250 to 500 times more stars than the Milky Way. If you tried to count every star in IC 1101, counting 1 star per second without sleeping or stopping, it would take you over 3 million years. 3 million years of constant counting, just to enumerate the stars in this single galaxy. IC 1101's classification has been debated by astronomers over the years. It is sometimes classified as a supergiant elliptical galaxy, sometimes as a supergiant lenticular galaxy, type S0, and sometimes simply as a CD galaxy without specifying the underlying type. The confusion arises because IC 1101 is so extreme that it does not fit neatly into normal classification schemes. Its central region has properties similar to both elliptical and lenticular galaxies, and the extended halo complicates any simple classification. One thing that is not debated is IC 1101's color. When astronomers observe the galaxy, it appears distinctly golden yellow. This color tells us something important about the stellar population. IC 1101 is dominated by old red stars. There is very little star formation happening in this galaxy. The blue young stars that light up the spiral arms of galaxies like the Milky Way are largely absent from IC 1101. This makes sense when you consider how IC 1101 likely formed. Through billions of years of mergers, the galaxy used up most of its gas. Star formation requires cold, dense gas that can collapse under its own gravity. Without gas, you cannot make new stars. IC 1101 burned through its gas long ago, leaving behind an ancient population of stars that have been slowly aging ever since. Some of the stars in IC 1101 are estimated to be around 7 billion years older than our Sun, making them about 11 to 12 billion years old. These are some of the oldest stars in the universe. In 2017, astronomers published a detailed study of IC 1101's structure that revealed something remarkable. The galaxy has an extraordinarily large core, measuring about 4.2 kiloparsecs, roughly 13,700 light-years, across. This is about 10 times larger than the cores of typical elliptical galaxies. Even more striking, this core appears to be depleted of stars compared to what models would predict. The depleted core is a signature of IC 1101's violent history. When galaxies merge, their central supermassive black holes spiral toward each other. As they do, they interact gravitationally with the surrounding stars, flinging some of them outward in a process called gravitational slingshot. Over multiple mergers, this process can clear out the central region of the galaxy, creating a depleted core. The fact that IC 1101's core is so large and so depleted suggests that this galaxy has undergone many major mergers throughout its history. How does IC 1101 compare to other galaxies? Let me paint some pictures for you. If you could somehow shrink the Milky Way down to the size of a dinner plate, about 10 inches across, then at the same scale, IC 1101's main body would be about the size of a large beach ball, roughly 2 to 3 feet across. But if you include the extended halo, IC 1101 would be the size of a small car. That is how much larger this galaxy is than our own. If IC 1101 replaced the Milky Way in our location, the night sky would be transformed beyond recognition. Instead of seeing a few thousand stars with the naked eye, we might see millions. The sky would glow with starlight. And the other major galaxies of the local group would no longer be distant smudges visible only through telescopes. They would be inside the galaxy, part of IC 1101's stellar population rather than independent systems. The light output of IC 1101 is equally impressive. This single galaxy produces about 26% of all the light emitted by the entire Able 2029 cluster. Think about that. The cluster contains hundreds of other galaxies, including many large elliptical and spiral galaxies, and yet IC 1101 alone produces more than a quarter of the total luminosity. It dominates its environment in a way that few other objects in the universe can match. IC 1101's position at the center of Able 2029 is not a coincidence. The galaxy sits at the bottom of the cluster's gravitational potential well, the lowest point in the cluster's gravity field. Over billions of years, galaxies that fall into the cluster tend to sink toward this central region, where they can be captured and consumed by IC 1101. The cluster is essentially feeding the central galaxy, delivering fresh material for it to absorb. This process is still ongoing. Astronomers have observed evidence that IC1101 is continuing to grow, still pulling in smaller galaxies and adding their stars to its own population. The galaxy is not done yet. It is still building itself, still getting larger, still consuming its neighbors. The Abell 2029 cluster itself is a fascinating object. It is classified as a cooling flow cluster, which means that the hot gas that fills the space between galaxies is slowly cooling and flowing inward toward IC1101. This gas, heated to tens of millions of degrees by the cluster's gravity, emits X-rays that can be detected by space telescopes like Chandra and XMM Newton. The cooling flow may help explain why IC1101 is so massive. The inflowing gas provides fuel that has helped the galaxy grow throughout cosmic history. The Abell 2029 cluster has a mass of approximately 5 to 8 times 10 to the 14th solar masses, making it one of the more massive galaxy clusters known. Most of this mass is not in the form of stars or gas that we can see. It is dark matter, the mysterious substance that does not emit or absorb light, but reveals its presence through gravity. The dark matter halo of Abell 2029 forms a vast, invisible structure within which the visible galaxies are embedded like plums in a pudding. The hot gas in the cluster, called the intra-cluster medium, has a temperature of about 100 million degrees Kelvin. At these temperatures, the gas emits powerful X-ray radiation. Observations show that this X-ray emission is strongly peaked at the location of IC1101, indicating that the gas is densest at the cluster center where IC1101 sits. The galaxy appears to be embedded in a cocoon of superheated plasma, fed by the enormous gravitational potential of the cluster. Scientists have used various wavelengths of light to study IC1101, from radio waves to X-rays. In radio observations, IC1101 shows a bright source at its center, associated with the activity of its supermassive black hole. This radio emission indicates that material is falling into the black hole and being accelerated to relativistic speeds before being ejected in jets. In optical wavelengths, we see the golden glow of its ancient stellar population, the light of hundreds of trillions of stars blended together into a smooth, featureless blur. In X-rays, we see the hot gas of the surrounding cluster, with IC1101 sitting like a bright pearl at the center of a glowing shell. Observations from the Hubble Space Telescope in 1994 provided the first high-resolution images of IC1101's core. These images revealed details that ground-based telescopes could not resolve, including the structure of the depleted core region. More recent observations have refined our understanding of the galaxy's mass distribution, velocity structure, and stellar population. All of these observations paint a picture of a galaxy that has reached the absolute extreme of what galaxies can become. IC1101 is not just big, it is the culmination of billions of years of cosmic evolution. It represents what happens when everything goes right for a galaxy, when the environment, the location, and the history all conspire to create something truly extraordinary. The galaxy sits in a privileged position at the bottom of a deep gravitational well, steadily consuming the resources that flow toward it. Growing ever larger while other galaxies around it remain stunted by comparison. And at the heart of this monster sits something even more extreme. A black hole so massive that it challenges our understanding of how such objects can form. That black hole is our next destination. Because if you thought IC1101 was intimidating, wait until you meet what lies at its center. At the center of almost every large galaxy lurks something both invisible and inescapable. A region where the laws of physics bend toward the extreme. a place where gravity becomes so intense that not even light can break free. We call these objects black holes, and they are among the most mysterious phenomena in the entire universe. But not all black holes are created equal. The black holes that form when massive stars die are impressive enough. They might contain the mass of 10 or 20 suns compressed into a sphere just a few miles across. Yet these stellar remnants are mere specks compared to the titans that sit at the hearts of galaxies. Supermassive black holes contain millions, sometimes billions of times the mass of our sun. They are gravitational anchors around which entire galaxies revolve. The Milky Way has one. Our galaxy's central black hole is called Sagittarius A star, and it weighs in at about 4 million times the mass of the sun. That might sound enormous, and it is. 4 million suns worth of matter crushed into a region smaller than the distance between Earth and the sun. Yet in the grand scheme of supermassive black holes, Sagittarius A star is rather modest. The black hole at the center of the galaxy M87 is a different story entirely. This is the black hole that made history in April 2019, when the Event Horizon Telescope collaboration released the first ever direct image of a black hole's shadow. That orange ring of fire that appeared on screens around the world showed us the silhouette of a monster. M87's black hole weighs approximately 6.5 billion times the mass of our sun. That is more than 1,000 times heavier than the black hole at the center of our own galaxy. But even M87's black hole, spectacular as it is, may not represent the upper limits of what the universe can produce. When astronomers turned their attention to IC 1101, they found something that pushes against the very boundaries of possibility. Deep within the core of IC 1101, hidden behind the glow of 100 trillion stars, sits a supermassive black hole of almost incomprehensible scale. Various measurement techniques have produced different estimates, but all of them point towards something extraordinary. The most commonly cited range puts the black hole's mass between 40 and 100 billion times the mass of our sun. Some studies using gas accretion rate modeling have suggested a mass in the range of 50 to 70 billion solar masses. Others have proposed figures as high as 97 billion solar masses. Let those numbers settle for a moment. We are talking about a single object that might contain the mass of 100 billion stars like our sun. If you gathered every star in the Milky Way and compressed them all into one point, you would still fall short of matching IC 1101's central black hole. This is not merely supermassive. Astronomers have started using a new term for objects of this scale: ultramassive. To put this in perspective, consider the comparison chain. Our sun is one star among hundreds of billions in the Milky Way. Sagittarius A star, our galaxy's central black hole, has the mass of 4 million suns. That means IC 1101's black hole could be somewhere between 10,000 and 25,000 times more massive than the black hole at the heart of our own galaxy. It could be 15 times heavier than M87's already enormous black hole. The existence of such an enormous black hole raises fascinating questions about the fundamental limits of the universe. Theoretical physicists have long debated whether there is a maximum size that a black hole can achieve through normal processes. The conventional wisdom suggests that black holes growing by swallowing surrounding gas face a practical ceiling of around 50 billion solar masses. Beyond this point, the physics becomes complicated. The accretion disk that feeds the black hole grows so massive and so large that it becomes gravitationally unstable. Instead of continuing to funnel matter into the black hole, the disk fragments and collapses into stars that orbit the black hole rather than falling into it. IC 1101's black hole appears to be right at, or perhaps even beyond, this theoretical limit. This suggests that something unusual happened during its growth. Perhaps multiple massive black holes merged together over billions of years, bypassing the accretion limit entirely. Perhaps the conditions in the early universe allowed for more extreme growth than our models predict. Or perhaps our understanding of the theoretical limits needs revision. The presence of IC 1101's black hole is not invisible to our instruments. At the center of the galaxy sits a powerful radio source cataloged as PKS 1508+059. Radio telescopes have detected this source for decades, and it tells us that the black hole is not entirely dormant. Material is still falling toward the event horizon, releasing energy in the process. When matter spirals toward a black hole, it does not simply disappear quietly. The gas and dust form a swirling disk that heats up to extreme temperatures as particles crash into each other at tremendous speeds. Some of this material gets twisted by magnetic fields and accelerated to nearly the speed of light, shooting outward in concentrated beams called jets. These jets can extend for thousands or even millions of light years, blasting through the surrounding space like cosmic blowtorches. The radio emissions from IC 1101's center are evidence of this activity. The black hole is still feeding, still growing, still influencing the galaxy around it. But the relationship between a supermassive black hole and its host galaxy runs deeper than mere feeding. Scientists have discovered a remarkable correlation that connects black holes to the galaxies they inhabit. This relationship is called the M-sigma relation, and it reveals something profound about how galaxies and their central black holes evolve together. The M-sigma relation shows that the mass of a black hole is tightly correlated with the velocity dispersion of stars in the surrounding galactic bulge. Velocity dispersion is essentially a measure of how fast stars are randomly moving in different directions. Galaxies with higher velocity dispersions tend to host more massive black holes. This correlation is surprisingly tight. It holds across many orders of magnitude and across different types of galaxies. The implication is striking. The black hole and the galaxy must somehow grow together, their fates intertwined. When the galaxy merges with other galaxies and grows larger, the black hole grows too. The mechanisms that build the galaxy also build its central black hole. For IC 1101, this relationship makes sense. The galaxy is enormous. Its stars move at high speeds through deep gravitational wells shaped by tremendous amounts of mass. If the M-sigma relation holds, IC 1101 should host one of the most massive black holes in the universe, and indeed, it does. But the black hole has left other traces of its presence. One of the most telling pieces of evidence comes from the structure of IC 1101's core. Unlike smaller galaxies, which often have dense concentrations of stars at their centers, IC 1101 has what astronomers call a depleted core. This is a region at the very heart of the galaxy where the stellar density is lower than you would expect. Something has carved out the center of this galaxy, flinging stars away from the innermost regions. A study published in 2017 measured IC 1101's core and found it to be the largest depleted core of any galaxy known. The core radius extends approximately 4.2 kiloparsecs, or about 13,700 light-years. That is an order of magnitude larger than the cores of other large elliptical galaxies. To visualize this, imagine a sphere at the center of the galaxy, 13,700 light-years across, where stars are mysteriously sparse. How did this enormous void form? The answer involves one of the most violent processes in the universe, the merging of supermassive black holes. When two galaxies merge, each brings its own central black hole to the union. These black holes do not collide instantly. Instead, they spiral toward each other over millions of years, sinking toward the center of the merged galaxy. As they draw closer, they form a binary system, two massive black holes orbiting their common center of mass. This binary becomes a gravitational wrecking ball. Stars that pass too close get caught in a cosmic game of pinball. Through a process called the gravitational slingshot effect, stars can steal energy from the binary's orbit. The star gets flung away at high velocity, while the black holes sink a little closer together. Over time, this process can eject enormous numbers of stars from the central region of the galaxy. Eventually, the black holes get close enough that gravitational waves take over. The space-time around the binary becomes so distorted that ripples propagate outward, carrying energy away. The black holes spiral together faster and faster until they finally merge in a cataclysmic event that releases more energy than all the stars in the observable universe combined, for just a fraction of a second. IC 1101 has clearly gone through this process many times. Each major merger brought a new massive black hole into the center. Each merger event carved out more stars from the core. The cumulative result is the enormous depleted core we observe today. Scientists have estimated the stellar mass deficit in IC 1101's core. Approximately 490 billion solar masses worth of stars have been ejected from the central region. Think about that number. Nearly 500 billion suns worth of stars were flung from the galaxy's heart by the gravitational interactions of merging black holes. These displaced stars now orbit at larger radii, contributing to the diffuse halo that surrounds IC 1101. By comparing the mass deficit to the expected mass ejected per merger, astronomers can estimate how many major mergers IC 1101 has undergone. The numbers suggest at least 10 major mergers, possibly many more. Each merger not only added mass to the galaxy, but also contributed to sculpting its current structure. The depleted core is a scar left by billions of years of cosmic violence. The event horizon of IC 1101's black hole, the boundary beyond which nothing can escape, is staggeringly large. The size of an event horizon scales directly with the mass of the black hole. For a black hole of 50 billion solar masses, the event horizon would extend roughly 150 billion kilometers from the center. For comparison, Pluto orbits our Sun at an average distance of about 5.9 billion kilometers. IC 1101's black hole event horizon could extend more than 20 times farther than Pluto's orbit. You could fit several solar systems inside the event horizon of this single black hole. Despite its enormous size, the black hole remains invisible to direct observation. We cannot see it because, by definition, no light escapes from within the event horizon. What we can see are its effects on the surrounding environment. The radio emissions, the depleted core, the velocity dispersion of stars, the structure of the galaxy itself, all of these are fingerprints left by a monster hiding in plain sight. The black hole at the center of IC 1101 represents one of the most extreme objects in the known universe. It stands near the upper limits of what the cosmos can produce through billions of years of growth and mergers. It has shaped the galaxy around it, carving out vast regions and flinging stars across space. And it continues to grow, slowly but steadily accreting material even now. Consider the sheer scale of the event horizon. For a black hole of 50 billion solar masses, the Schwarzschild radius, which defines the event horizon for a non-rotating black hole, would be about 150 billion kilometers. Light traveling at 300,000 kilometers per second would take about 5.5 days to cross from one side of the event horizon to the other. Neptune orbits our Sun at an average distance of about 4.5 billion kilometers. IC 1101's black hole event horizon could swallow Neptune's entire orbit more than 30 times over. The density inside the event horizon defies intuition. Paradoxically, larger black holes have lower average densities within their event horizons. A black hole of 50 billion solar masses, if you calculated its average density by dividing its mass by the volume within the event horizon, would actually be less dense than air. This seeming contradiction arises because volume increases as the cube of the radius, while mass only increases linearly with radius for black holes. The practical effect is that, theoretically, you would not be torn apart by tidal forces as you cross the event horizon of IC 1101's black hole. You would feel nothing unusual at the moment of crossing. Only afterward, as you fell deeper toward the singularity, would the extreme gravity become apparent. Of course, once inside, there would be no escape. The radio source PKS 1508+059 at the galaxy's center tells us that the black hole is still active, still consuming material, still growing. The jets emanating from the nucleus carry energy across vast distances, heating the surrounding gas and influencing star formation in ways that extend far beyond the central black hole's immediate gravitational domain. This is AGN feedback in action, the process by which black holes regulate the growth of their host galaxies. When you contemplate IC 1101, you are not just thinking about a galaxy. You are thinking about the relationship between galaxies and the dark hearts that define them. The black hole and the galaxy have evolved together, each shaping the other across cosmic time. They are not separate phenomena, but two aspects of a single, interconnected system that has been building itself for billions upon billions of years. Galaxies do not simply appear fully formed in the universe. They are built over billions of years through a process that cosmologists call hierarchical structure formation. The universe started out remarkably smooth, with matter spread almost evenly across space. But tiny variations in density, quantum fluctuations stretched to cosmic scales by the expansion following the Big Bang, seeded the structures we see today. In regions where matter was ever so slightly denser than average, gravity began to pull things together. Dark matter, that mysterious substance that makes up most of the mass in the universe, clumped first. It formed halos, vast concentrations of invisible matter that acted as gravitational scaffolding for everything that followed. Ordinary matter, the atoms and molecules that make up stars and planets and people, fell into these dark matter wells. Gas collected at the centers of halos, cooled, and collapsed into the first stars and the first small galaxies. These early galaxies were nothing like the giants we see today. They were small, perhaps containing only a few billion stars. But they did not remain isolated for long. The same gravity that drew them together continued to work. Smaller galaxies fell into larger ones. Halos merged with other halos. Over billions of years, through countless collisions and mergers, galaxies grew larger and more massive. This process is what cosmologists mean when they talk about hierarchical assembly. The structures we see today are built from smaller structures that came before. Small galaxies merge to form medium-sized galaxies. Medium galaxies merge to form large galaxies. And in the densest regions of the universe, where matter concentrated most heavily, the largest galaxies of all could emerge. IC 1101 represents the extreme end of this process. It did not become the largest traditional galaxy in the known universe through gentle growth and quiet star formation. It grew by consuming other galaxies. It is, in the most literal sense, a cosmic cannibal. The evidence for IC 1101's merger history is written across its structure. Start with its position. IC 1101 sits at the exact center of the Abell 2029 galaxy cluster, one of the densest concentrations of galaxies in our cosmic neighborhood. This is no coincidence. Physics dictates that the most massive galaxy in a cluster will sink toward the gravitational center over time. As galaxies orbit within the cluster, they lose energy through a process called dynamical friction. This friction is not like the friction you experience when sliding across a floor. Instead, it arises from gravitational interactions. A massive galaxy moving through a field of other galaxies and dark matter creates a wake behind it, and this wake exerts a backward pull that gradually drains the galaxy's orbital energy. The result is that the most massive galaxies slowly spiral toward the cluster center, where they accumulate at the bottom of the gravitational well. IC 1101 has been sitting at this privileged position for billions of years, acting like a drain at the bottom of a cosmic bathtub. Any galaxy that loses enough orbital energy eventually falls toward the center, where IC 1101 is waiting to absorb it. Look around IC 1101 in the cluster, and you will notice something interesting. There are no other large bright galaxies nearby. The immediate vicinity of IC 1101 is curiously empty of significant companions. They have been eaten. Over billions of years, IC 1101 has consumed every substantial galaxy that ventured too close. The stellar populations of those destroyed galaxies now orbit within IC 1101's vast halo, their original identities erased by time and gravity. The smoothness of IC 1101's halo provides further evidence. When galaxies merge, the collision initially creates dramatic structures. Tidal tails stretch outward as gravity tears the merging galaxies apart. Shells and streams of stars form as material gets thrown around. But these features are temporary. Over hundreds of millions of years, the stars settle into new orbits. The evidence of the merger gets smoothed away. A galaxy that has undergone many mergers over a very long time will appear remarkably smooth and uniform, its violent history hidden behind a serene exterior. IC 1101 is exactly this smooth. Its light falls off in a regular pattern from the bright center to the faint outer halo. There are no obvious streams or shells that would indicate a recent major merger. This does not mean IC 1101 stopped eating. It means the last truly disruptive mergers happened long enough ago that the galaxy has had time to digest its meals and settle back into equilibrium. The depleted core we discussed in the previous section also speaks to IC 1101's merger history. Each time a major merger brought another supermassive black hole into the galaxy's center, the resulting binary black hole ejected stars through the gravitational slingshot effect. The enormous mass deficit, nearly 490 billion solar masses worth of displaced stars, implies many such merger events. Conservative estimates suggest at least 10 major mergers, but the true number could be significantly higher if we include intermediate mass mergers that contributed to the core scouring. Astronomers distinguish between different types of galaxy mergers based on the gas content of the merging systems. A wet merger involves gas-rich galaxies. When these collide, the gas gets compressed and heated, triggering intense bursts of star formation. A wet merger might produce billions of new stars in a relatively short period, temporarily transforming the merged galaxy into a spectacular starburst system. A dry merger, by contrast, involves gas-poor galaxies, typically elliptical galaxies that have already used up or lost most of their star-forming material. When these collide, there is little gas to compress and no starburst. Instead, the merger primarily redistributes the existing stellar populations. The stars from both galaxies get mixed together, and the combined galaxy becomes larger without forming many new stars. IC 1101 has likely experienced both types of mergers throughout its history, but its recent merger activity has been predominantly dry. The evidence supports this conclusion. IC 1101 is essentially a dead galaxy in terms of star formation. It has very little cold gas available to form new stars. Its stellar population is old, dominated by red giant stars and other evolved objects. If IC 1101 were still undergoing wet mergers, we would see more star formation, younger stellar populations, and traces of recent gas compression. The dominance of dry mergers makes sense given IC 1101's environment. As the central galaxy in a massive cluster, it is surrounded primarily by other elliptical galaxies and gas-poor systems. Spiral galaxies, with their abundant reserves of star-forming gas, are rare in the dense cores of clusters. They tend to lose their gas through processes like ram pressure stripping as they move through the hot intracluster medium. By the time a galaxy falls close enough to IC 1101 to be consumed, it has usually already lost most of its gas and transformed into a red, quiescent system. This pattern of dry mergers has important consequences for IC 1101's structure. Dry mergers are dissipationless, meaning that energy is not efficiently radiated away during the collision. Instead of settling into a flat rotating disk, the merged stellar population maintains random, chaotic orbits. This is why IC 1101 is elliptical rather than spiral. The cumulative effect of many dry mergers has produced a galaxy supported by random stellar motions rather than organized rotation. But the merging process does not only involve visible galaxies. Dark matter plays a crucial role. Each galaxy that IC 1101 has consumed brought with it a dark matter halo. These halos merged along with their visible counterparts, adding to IC 1101's invisible mass. The dark matter halo around IC 1101 is enormous, extending far beyond the visible stars and containing many times more mass than the luminous component of the galaxy. This dark matter halo is what truly anchors IC 1101 to the center of Able 2029. The gravitational pull of the combined dark matter from all the merged halos keeps IC 1101 firmly planted at the bottom of the cluster's potential well, and the dark matter continues to guide new material toward the galaxy, funneling galaxies and gas along the filaments of the cosmic web. Dark matter is the invisible scaffolding of the universe. We cannot see it directly because it does not interact with light, but we can measure its presence through its gravitational effects. Stars and galaxies rotate faster than they should based on the visible mass alone. Galaxy clusters contain far more mass than the visible galaxies can account for. The large-scale structure of the universe, with its filaments and voids, requires dark matter to explain how gravity pulled things together in the time since the Big Bang. IC 1101 is embedded in an enormous cocoon of dark matter. The dark matter halo around the galaxy extends far beyond the visible stars, possibly reaching scales comparable to the entire cluster. This invisible mass dominates the gravitational dynamics of the system. When we talk about IC 1101's total mass, including dark matter, we are talking about something vastly larger than the stellar mass alone. The cosmic web is the largest scale structure in the universe. It consists of vast filaments of dark matter and gas connecting dense nodes where galaxy clusters form. The nodes are like the intersections in a three-dimensional spider web, and the filaments are the strands stretching between them. Matter flows along these filaments, gradually accumulating at the nodes. Able 2029 sits at one such node. Galaxies and gas stream toward it along multiple filaments, providing a continuous supply of material for IC 1101 to potentially consume. In fact, Astronomers have detected evidence that Able 2029 is currently merging with a nearby cluster, Able 2033. This cluster-scale merger will eventually bring new galaxies into IC 1101's hunting grounds. The violence of galaxy mergers extends beyond the stellar components. When galaxies collide, their central supermassive black holes are eventually brought together. The black holes do not merge instantly. First, they sink toward the center of the merged galaxy through dynamical friction. Then, they form a binary system orbiting each other at separations of a few parsecs. Finally, through continued stellar interactions and gravitational wave emission, they merge into a single, more massive black hole. These black hole mergers are among the most energetic events in the universe. The final moments of in-spiral and coalescence release tremendous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. We cannot currently detect gravitational waves from IC 1101's black hole mergers because they happened billions of years ago and the signals have long since passed Earth. But we can infer their occurrence from the scouring of the galactic core and the growth of the central black hole. Each black hole merger added mass to IC 1101's central black hole. Each merger event ejected stars from the core. The process was repeated again and again over cosmic time, building up the ultramassive black hole we observe today and creating the enormous depleted core. The evidence thus paints a consistent picture. IC 1101 grew to its current size through billions of years of galactic cannibalism. It consumed countless smaller galaxies, absorbing their stars, dark matter, and black holes. Its position at the center of a massive galaxy cluster provided a steady stream of victims, while its growing mass made it ever more effective at capturing and consuming new material. And the process is not finished. IC 1101 is still growing today. Astronomers estimate that the galaxy accretes roughly 450 solar masses of material per year. That might sound like a lot, but for a galaxy of IC 1101 size, it represents a slow drip rather than a flood. The growth rate has decreased as the galaxy has consumed most of the available nearby material. But over billions of additional years, IC 1101 will continue to add mass, continue to dominate its environment, and continue its existence as the ultimate product of hierarchical galaxy assembly. The gravitational waves produced during black hole mergers represent another fascinating aspect of IC 1101's history. When supermassive black holes spiral together and merge, they release tremendous energy in the form of gravitational waves. These ripples in space-time propagate outward at the speed of light, carrying information about the merger across the cosmos. The gravitational waves from IC 1101's ancient black hole mergers passed through our location in space billions of years ago, long before Earth or even the Sun existed. We cannot detect them now, but future gravitational wave observatories operating at extremely low frequencies, using arrays of pulsars as cosmic detectors, might be able to detect similar signals from other massive galaxy mergers occurring today. The story of IC 1101 is the story of how structure forms in our universe. It is a story of gravity and time, of small things combining into larger things, of relentless accumulation over cosmic ages. When you look at IC 1101, you are seeing the end result of this process, taken to its extreme. You are seeing what happens when a galaxy is given enough time, enough material, and the perfect position to grow without limit. You are seeing a cannibal king on its throne at the heart of its domain, built from the remains of all its victims. In February 2022, headlines around the world announced a startling discovery. Astronomers had found what they called the largest galaxy ever discovered. Its name was Alcyonius, after one of the giants from Greek mythology who battled the Olympian gods. The structure stretched an almost incomprehensible 16 million light-years across space. That is 160 times the diameter of our Milky Way, enough to fit over 100 of our home galaxies end to end. But here is where the story gets interesting, and where we need to be careful about what we mean by largest. Alcyoneus is what astronomers call a giant radio galaxy. It consists of a host galaxy at the center, with two enormous jets of plasma erupting from its core, powered by a supermassive black hole. These jets extend far beyond the galaxy itself, eventually spreading out into diffuse lobes that glow in radio wavelengths. When astronomers talk about Alcyoneus being 16 million light-years across, they are measuring from the tip of one radio lobe to the tip of the other, passing through the relatively small host galaxy in the middle. The host galaxy of Alcyoneus, the actual stellar body where billions of stars reside, is far more modest in size. It has an isophotal diameter of about 240,000 light-years. That is roughly twice the size of the Milky Way, which makes it a large galaxy but hardly exceptional. Compared to IC 1101, the host galaxy of Alcyoneus is almost mundane. IC 1101's stellar body, even measured conservatively, is at least 400,000 to 550,000 light-years across, with its diffuse halo extending to millions of light-years. This distinction matters because it highlights the different ways we can measure galaxy size. The radio lobes of Alcyoneus are not made of stars. They are clouds of relativistic particles, electrons, and other charged matter, accelerated to nearly the speed of light by the magnetic fields around the central black hole. These particles spiral through space and emit radio waves through a process called synchrotron radiation. The lobes are impressive structures, certainly, and they tell us something important about the power of the black hole at Alcyoneus's center. But they are not the galaxy itself in any traditional sense. This is why, despite the headlines, IC 1101 remains the largest known galaxy in terms of its stellar body and total gravitational mass. When we talk about IC 1101, potentially extending 4 to 6 million light-years, including its diffuse halo, we are talking about actual stars, actual mass, actual gravitational influence. The comparison between Alcyoneus and IC 1101 is a bit like comparing the length of a garden hose's spray to the size of a swimming pool. Both are impressive, but they are measuring fundamentally different things. The discovery of Alcyoneus came from a team led by Martijn Ooi of Leiden University, using data from the Low-Frequency Array, or LOFAR, a vast network of radio antennas spread across Europe. By reprocessing images from the LOFAR 2-meter sky survey, the team was able to detect faint radio emissions that previous searches had missed. Alcyoneus was hiding in plain sight, its diffuse lobes too faint to be noticed in earlier, less sensitive searches. What makes Alcyoneus scientifically fascinating is not just its size, but how ordinary the host galaxy appears. The central galaxy does not have an unusually massive black hole. It does not have an unusually powerful jet. Its stellar population is not exceptional. By most measures, the host galaxy of Alcyoneus is average for a giant radio galaxy. Yet somehow, its jets have grown to unprecedented lengths. The most likely explanation involves Alcyoneus's environment. The galaxy appears to reside in a region of the cosmic web that is less dense than average. With fewer obstacles in their path, the jets could expand more freely, spreading over greater distances before their energy dissipated. Alcyoneus may owe its record size not to any exceptional property of the galaxy itself, but to the fortunate accident of living in a relatively empty neighborhood. Alcyoneus held its record for only about 2 years. In September 2024, Another team led by the same Martin Oey announced the discovery of an even larger giant radio galaxy. They called it Porphyrion, named after another of the Greek giants. Porphyrion's radio jets span an astounding 23 million light-years, making it nearly 50% larger than Alcyonius. The discovery of Porphyrion came with a twist. Unlike Alcyonius, which exists in the relatively nearby universe, Porphyrion is 7.5 billion light-years away. We are seeing it as it appeared when the universe was only about 6.3 billion years old, less than half its current age. At that time, the cosmic web was denser. Galaxies were closer together. The filaments that connect clusters were more tightly packed. Yet even in this more crowded environment, Porphyrion managed to extend its jets to extraordinary lengths. Porphyrion's existence suggests that giant jets were more common in the early universe than astronomers previously thought. These enormous structures may have had profound effects on their surroundings, injecting energy and magnetic fields into the intergalactic medium, potentially influencing the formation and evolution of other galaxies over vast distances. The jets of Porphyrion are almost perfectly straight, which is surprising. Jets can be bent by collisions with dense material, by changes in the orientation of the black hole, or by magnetic forces. The fact that Porphyrion's jets remain so linear over 23 million light-years suggests remarkably stable conditions in both the black hole and its environment. The black hole at Porphyrion's center has been consistently oriented for the billion years it took the jets to grow to their current length. The space through which the jets passed must have been relatively clear of obstructions. The power output of Porphyrion's jets is staggering. Combined, the two jets release energy equivalent to trillions of suns. This energy comes from the accretion process around the central black hole. As matter falls toward the black hole, it releases gravitational potential energy. Some of this energy escapes as radiation. Some gets channeled into the jets through complex processes involving magnetic fields and relativistic physics. The black hole is essentially a cosmic engine, converting the gravitational infall of matter into concentrated beams of energy and particles that reshape the surrounding universe. The LOFAR surveys that found Alcyonius and Porphyrion have detected more than 10,000 radio galaxies with jets spanning at least 3 million light-years. This population of megajets was largely unknown before the era of sensitive wide-field radio surveys. The universe, it seems, is full of galaxies belching fire across millions of light-years of space. But again, the stellar bodies of these galaxies, the actual collections of stars that we traditionally call galaxies, remain much smaller than their spectacular radio emissions. Beyond the radio giants, several other galaxies compete for the title of largest stellar body. The Condor Galaxy, also known as NGC 6872, is one of the largest spiral galaxies known. Its spiral arms stretch approximately 522,000 light-years from tip to tip, giving it a span about 5 times that of the Milky Way. But the Condor Galaxy has been stretched by a gravitational interaction with a companion galaxy. Its extreme length is partly an artifact of this tidal distortion rather than intrinsic size. Malin 1 is a peculiar giant low-surface brightness galaxy discovered in 1986. It has a disk extending roughly 650,000 light-years in diameter, making it the largest spiral galaxy measured in some surveys. But its surface brightness is so low that it is almost invisible. Most of its disk contains very few stars per unit area. The total stellar mass of Malin 1 is far less than what its diameter would suggest. Among elliptical galaxies, A2261 BCG in the Abell 2261 cluster rivals IC 1101 for size. Its core is one of the largest known, measuring about 10,000 light-years across, and its total size is comparable to IC 1101's. Interestingly, astronomers have struggled to find the expected supermassive black hole at the center of A2261 BCG. Either the black hole is unusually faint, or it may have been ejected from the galaxy's center through gravitational wave recoil following a black hole merger. The galaxy represents another example of the extreme outcomes possible in the centers of massive clusters. The diversity of these giants illustrates the many ways to define galactic size. You can measure the extent of radio emissions, which gives you Porphyrion and Alcyonius. You can measure the stretched arms of a spiral, which gives you the Condor galaxy. You can measure the diffuse disk of a low-surface brightness galaxy, which gives you Malin 1. You can measure the stellar mass and gravitational influence, which gives you IC 1101. Each measurement tells us something different about these cosmic structures. Radio emissions tell us about black hole activity and jet power. Spiral arm extent tells us about tidal interactions and angular momentum. Surface brightness profiles tell us about star formation history and dark matter distribution. Total mass tells us about hierarchical assembly and merger history. The challenge of measuring galaxy size is not just philosophical, but practical. Galaxies do not have sharp edges. They fade gradually from bright centers to dim halos, and different telescopes with different sensitivities will see different amounts of this fading glow. A galaxy photographed with a small telescope for a short time will appear smaller than the same galaxy photographed with a large telescope for a long time. This is why astronomers have developed standardized measurement techniques like the isophotol diameter, which measures the galaxy out to a specific surface brightness level. Even then, different wavelengths of light reveal different aspects of the galaxy. Infrared light penetrates dust and reveals the distribution of old, cool stars. Ultraviolet light traces young, hot stars and star formation. Radio waves show the jets and halos powered by black hole activity. IC 1101 has been measured using many of these techniques. Its isophotol diameter at standard surface brightness thresholds gives a size of 400,000 to 550,000 light-years. Deep imaging that pushes to fainter surface brightness levels reveals the extended halo stretching to millions of light-years. Each measurement adds to our understanding of this remarkable object. By most measures that relate to the actual content and gravitational significance of a galaxy, IC 1101 remains the champion. Its stellar mass is among the highest of any galaxy measured. Its gravitational influence extends across millions of light-years. Its dark matter halo is enormous, and it sits at the center of a massive galaxy cluster, the culmination of billions of years of cosmic growth. But the universe continues to surprise us. The James Webb Space Telescope is revealing galaxies in the early universe that are far larger and more massive than our models predicted. Deep surveys keep finding larger and larger structures in unexpected places. It is entirely possible that somewhere in the cosmos, there exists a galaxy even more massive than IC 1101 waiting to be discovered. The search for the largest galaxy is not merely a competition for records. Each giant galaxy we find teaches us something new about how the universe builds structure. Porphyrion tells us about black hole activity in the early universe. Alcyonius tells us about the influence of cosmic environment on jet propagation. IC 1101 tells us about the extreme outcomes of hierarchical merging in dense cluster cores. Together, these giants form a gallery of cosmic extremes, each representing a different path that matter and energy can take as the universe evolves. They remind us that the cosmos operates on scales that dwarf human comprehension, that the same physical laws that govern our everyday lives can produce structures spanning millions of light years, and that even after centuries of astronomical observation, the universe still has secrets waiting to be uncovered. The race to find the largest structures continues. New telescopes, new surveys, and new techniques will almost certainly reveal giants that we cannot yet imagine. The Vera C. Rubin Observatory, currently under construction in Chile, will survey the entire visible sky repeatedly over 10 years, cataloging billions of galaxies and potentially finding new record holders. The Square Kilometre Array, a radio telescope being built across Africa and Australia, will detect radio emissions far fainter than current instruments can see. Who knows what titans lurk in the darkness, waiting to be revealed? The competition for records is not merely academic vanity. Each discovery teaches us something new about the range of possibilities in our universe. When we find a galaxy larger than any seen before, we are not just adding to a list. We are expanding our understanding of what galaxies can be, how they can form, and what the universe is capable of creating. But for now, when we speak of the largest traditional galaxy in terms of stellar mass and gravitational dominance, IC 1101 stands alone. It is the king of galaxies, and it earned its throne through billions of years of cosmic cannibalism in one of the densest environments the universe has to offer. There is a certain irony in calling the largest galaxy a dying giant. IC 1101 contains more stars than almost any other galaxy we know of. It dominates its environment. It continues to grow, slowly absorbing material from its surroundings. And yet, in the language of astronomers, IC 1101 is dead. Or more precisely, it is dying. What does death mean for a galaxy? It has nothing to do with the stars themselves, which will continue burning for billions or trillions of years. Galaxy death refers to something more specific, the cessation of star formation. A living galaxy is one that actively converts gas into new stars. A dead or dying galaxy is one where this process has largely stopped. The Milky Way is alive. Right now, as you read this, massive clouds of gas in the spiral arms of our galaxy are collapsing under their own gravity. New stars are being born. Some of those stars will live for billions of years, while others will explode as supernovae within a few million years, enriching the surrounding gas with heavy elements and triggering further waves of star formation. Our galaxy creates roughly 2 new stars per year, continuing a process that has been running for more than 13 billion years. IC 1101 has essentially stopped. The rate of new star formation in IC 1101 is negligible compared to its enormous size. The galaxy is not making new stars at any meaningful rate. Instead, it is slowly using up its existing stellar population. As old stars die, they are not being replaced by young ones. You can see this in the color of the galaxy. IC 1101 glows with a warm golden yellow hue, the combined light of hundreds of trillions of aging stars. Young, massive stars burn hot and blue, but they live fast and die young. A galaxy with active star formation shows blue tinges where those young stars illuminate their surroundings. IC 1101 shows no such blue light. Its stellar population is old, dominated by red giants, orange dwarfs, and other long-lived stars that have been burning for billions of years. Some of IC 1101's stars are ancient beyond easy comprehension. Studies of the galaxy's stellar population suggest that some stars are as much as 7 billion years older than our Sun. Given that our Sun formed about 4.6 billion years ago, these stars came into being when the universe was only 2 or 3 billion years old. They witnessed the formation of the galaxy itself and have been quietly shining ever since. Why did IC 1101 stop forming stars? The answer involves several interconnected factors, each reinforcing the others. First, the gas is gone. Star formation requires cold, dense molecular gas, the raw material from which stars condense. Through billions of years of mergers, IC1101 has consumed or expelled most of its gas. The wet mergers early in the galaxy's history triggered intense starbursts that used up vast quantities of gas. The dry mergers that followed added stellar mass but brought little new gas. Any remaining gas was either consumed in these mergers or heated to temperatures too high for star formation. The molecular clouds that form stars in galaxies like the Milky Way are extraordinarily cold, often just a few degrees above absolute zero. At these temperatures, gas molecules move slowly enough that gravity can pull them together. The slightest warming disrupts this process. In IC1101, the ambient temperature of any remaining gas is far too high. The galaxy is permeated by hot plasma at millions of degrees, a reservoir of thermal energy that prevents gas from cooling and collapsing. Second, the environment is hostile to gas retention. IC1101 sits at the center of the Abell 2029 cluster, immersed in a bath of extremely hot plasma called the intracluster medium. This gas, heated to tens of millions of degrees, fills the space between galaxies in the cluster. Any cold gas that might fall toward IC1101 gets heated by interaction with this hot medium long before it can reach the galaxy and form stars. Third, the central black hole has played a role in suppressing star formation. Feedback from the active galactic nucleus, when the black hole was more active, injected energy into the surrounding gas. This energy heated the gas and prevented it from cooling and collapsing into stars. Even today, with the black hole relatively quiet, residual heating from past activity maintains the quiescent state. This process is called AGN feedback, and it is one of the primary mechanisms that cosmologists invoke to explain why massive galaxies stop forming stars. The combination of these factors has created a galaxy that is essentially frozen in time. The stars that exist will continue to evolve according to their individual properties, but no new generation will arise to replace them. IC1101 is living off its accumulated wealth of stars, slowly spending down its stellar inheritance with no way to replenish it. There is one exception to this picture of complete quiescence. IC1101 still grows, but not through star formation. It grows by consuming other galaxies. The estimated accretion rate of about 450 solar masses per year does not come from gas collapsing into new stars. Instead, it comes from smaller galaxies and stellar material falling into IC1101's gravitational embrace. The galaxy is still eating, but it is eating already formed stars, not making new ones. This mode of growth is the only way IC1101 can survive in any meaningful sense. A galaxy that stops forming stars will eventually fade as its stars burn out. The massive stars die first, exploding as supernovae or collapsing into neutron stars and black holes. The medium-mass stars like our Sun will last for 10 billion years or so before swelling into red giants and shedding their outer layers. But even the smallest stars, the red dwarfs that burn their hydrogen fuel so slowly that they can last for trillions of years, will eventually exhaust themselves. Without new stars to replace the dying ones, IC1101 will grow dimmer over cosmic time. The golden glow will fade. The 100 trillion stars will dwindle as each reaches the end of its life cycle. In the far, far future, unimaginably distant from now, IC1101 will be a faint ghost of its current self, a vast collection of stellar corpses drifting through an increasingly dark universe. But that future is so distant that it barely registers on any meaningful human scale. IC1101 still has billions of years of relative vitality ahead of it. The universe itself is only 13.8 billion years old. IC 1101 will continue shining for many times that span, slowly fading but never quite extinguished. What does IC 1101's fate tell us about the future of our own galaxy? The Milky Way is very much alive today, but it will not remain so forever. In approximately 4 to 5 billion years, our galaxy is expected to collide with the Andromeda Galaxy. Recent studies have introduced some uncertainty about whether this collision is truly inevitable, with newer calculations suggesting the probability might be closer to 50%, depending on the gravitational influences of other local group galaxies. But if the collision occurs, it will fundamentally transform both galaxies. The collision itself will not destroy either galaxy. Stars are so widely separated that actual stellar collisions will be extremely rare. But the gravitational interaction will scramble the orderly rotation of both spiral disks. Tidal forces will tear long streamers of stars from each galaxy. Gas clouds will collide, compress, and trigger intense bursts of star formation. For a billion years, the merger will produce spectacular light shows as the two galaxies dance around each other, pulling apart and coming back together again and again. Eventually, the two galaxies will settle into a single, merged system. Astronomers have given this hypothetical future galaxy a name, Milkomeda, or sometimes Milkdromeda. It will most likely be an elliptical galaxy, its original spiral structure destroyed by the violence of the merger. The central black holes of the Milky Way and Andromeda will eventually merge, creating a more massive single black hole. The night sky, as seen from any surviving planets in Milkomeda, will look dramatically different from what we see today. Instead of the band of the Milky Way stretching across the sky, observers would see a diffuse glow from the central bulge of the merged elliptical galaxy. Constellations, as we know them, would be scrambled beyond recognition. The stars that form familiar patterns flung into completely different arrangements by the gravitational chaos of the merger. Milkomeda may bear some resemblance to IC 1101, though on a smaller scale. It will be an elliptical galaxy formed by the merger of two large spirals. It will have consumed its gas during the merger-triggered starburst. It will eventually cease forming stars and begin its long, slow fade. Could Milkomeda ever grow to rival IC 1101? Almost certainly not. The local group where we reside is not dense enough, not massive enough, to provide the steady stream of victims that fed IC 1101's growth. Milkomeda will be a large galaxy by local standards, but it will never dominate a cluster the way IC 1101 dominates Abell 2029. IC 1101 stands as a preview of one possible endpoint for galaxy evolution. It shows us what happens when a galaxy is given the resources and the time to grow without limit. It shows us the quiescence that follows billions of years of mergers and star formation. It shows us the slow fade that awaits all galaxies in the fullness of cosmic time. The universe itself faces an ultimate fate that makes even IC 1101's dimming seem modest. Current cosmological models predict that the universe will continue expanding forever, and that this expansion will gradually isolate galaxies from each other. Clusters will remain bound by gravity, but the space between clusters will stretch until distant galaxies disappear beyond our cosmic horizon. Within clusters, galaxies will eventually merge into single, enormous structures. All the galaxies in Abell 2029 will ultimately combine with IC 1101, creating an even larger dead elliptical. But even this supergalaxy will fade, over timescales measured in trillions of years. Stars will burn out. Black holes will slowly evaporate through a process called Hawking radiation, losing mass particle by particle over incomprehensible spans of time. In the very, very end, the universe will approach a state of maximum entropy called heat death. All energy will be spread so evenly that no processes can occur, no stars will shine, no planets will orbit. The cosmos will be cold, dark, and unchanging. This fate lies so far in the future that timescales become almost meaningless. We are talking about periods of time that make the current age of the universe, 13.8 billion years, look like an eye blink. Red dwarf stars can burn for trillions of years, steadily fusing their hydrogen at rates so slow that they barely warm their surroundings. White dwarfs, the cooling embers of dead sun-like stars, will gradually radiate away their remaining heat over quadrillions of years. Black holes will persist for inconceivable spans before finally evaporating. IC 1101 will be long gone by then, its stars extinguished, its black holes evaporated, its mass scattered across the void. But that end is so far in the future that it holds little relevance for us today. What matters is that IC 1101 exists now. It shines now. We can observe it and learn from it now. In observing IC 1101, we observe our own cosmic future, not in detail, not in certainty, but in broad outline. Galaxies grow, galaxies merge, galaxies stop forming stars, galaxies fade. This is the arc of galactic life, and IC 1101 represents one of the most advanced stages of that journey that we have yet observed. The dying giant is not yet dead. It has billions of years of existence ahead of it, and in those years, it will continue to teach us about the nature of the universe, the processes that build structure, and the ultimate fate of all the matter that gathered together under gravity's patient pull. We have come a long way in this journey. We started on Earth, a small rocky world orbiting an ordinary star in an unremarkable arm of a fairly typical spiral galaxy. We expanded our view to encompass the Milky Way, with its hundreds of billions of stars spread across 100,000 light years. We pushed further to the realm of galaxies beyond our own, where Andromeda glows in our night sky and the universe opens up into staggering immensity. And finally, we arrived at IC 1101, a galaxy so vast that it challenges our ability to comprehend scale. Let us take one more moment to appreciate what we have learned. IC 1101 is a supergiant elliptical galaxy lying at the center of the Abell 2029 cluster, approximately 1.15 billion light-years from Earth. Its stellar body spans at least 400,000 to 550,000 light-years in diameter, with a diffuse halo that may extend to 4 to 6 million light-years across. It contains an estimated 100 trillion stars, roughly 250 to 500 times as many as our Milky Way. At its heart lurks a supermassive black hole of 40 to 100 billion solar masses, one of the most massive known to exist. The galaxy has consumed countless smaller galaxies over billions of years, growing ever larger through relentless cosmic cannibalism. And despite its immense size, it is a dying giant, no longer forming new stars, slowly fading as its existing stellar population ages. When William Herschel looked through his telescope on that June night in 1790, he saw nothing more than a faint, fuzzy patch in the constellation Virgo. He had no way of knowing what he was looking at. The concept of galaxies did not exist. The idea that the universe contained billions of separate island universes, each home to countless stars, would have seemed like fantasy. Herschel recorded his observation and moved on, leaving the mystery for future generations to solve. Over the centuries that followed, astronomers slowly assembled the pieces of the puzzle. They debated whether spiral nebulae were part of our galaxy or separate systems entirely. They measured distances using Cepheid variables and discovered that the universe was far larger than anyone had imagined. They cataloged galaxies by the thousands, then by the millions, then by the trillions. They built telescopes in space to see beyond Earth's atmosphere, and telescopes on mountaintops to pierce the darkness between stars. Each generation contributed something to our understanding. Each discovery built upon those that came before. The knowledge that allows us to describe IC 1101 in such detail is not the work of any single person or any single era. It is the accumulated achievement of countless scientists working across centuries, each adding their piece to a growing mosaic of cosmic understanding. Think about the chain of knowledge that connects William Herschel's first observation to our current understanding. Herschel did not know what he was seeing, but he recorded it carefully. Later, astronomers identified it as something beyond the Milky Way. Spectroscopists measured its redshift and calculated its distance. Photographers captured its light on ever more sensitive plates and sensors. Theorists developed models of galaxy formation and evolution. Each link in this chain was essential. Remove any one of them, and our understanding of IC 1101 would be diminished. This collaborative nature of science is one of its greatest strengths. No single human mind could contain all the knowledge necessary to study a galaxy a billion light-years away. But many human minds, working together across generations and continents, can build understanding that transcends any individual. The international collaboration that operates the Event Horizon Telescope, the teams that analyze data from the Hubble Space Telescope, the theorists who run supercomputer simulations of galaxy evolution, all of them contribute to our understanding of objects like IC 1101. Consider what this achievement represents. We are tiny creatures living brief lives on a small planet in an ordinary solar system. Our entire species has existed for perhaps 300,000 years, a cosmic eye blink. Yet we have reached out across 1.15 billion light-years of space and learned the properties of a galaxy. We know how many stars it contains. We know the mass of its central black hole. We know the history of its growth and the nature of its eventual fate. This is extraordinary. The gap between the scale of human existence and the scale of IC 1101 is so vast that no analogy can truly bridge it. We are comparing sand grains to oceans, heartbeats to geological ages, whispers to thunderclaps. And yet the comparison can be made. The universe is comprehensible. Physics works the same way here as it does a billion light-years away. Light carries information across unimaginable distances, and patient observation can decode that information into knowledge. IC 1101 will never know that we discovered it. Galaxies do not have minds. They do not experience awareness. The 100 trillion stars that make up IC 1101 burn according to the laws of nuclear physics, indifferent to whether anyone is watching. But we know. We are aware. We have looked out across the cosmos and recognized something of what we are seeing. There is a beautiful thought experiment that captures this idea. The atoms in your body were forged in stars. The carbon that makes up your muscles, the oxygen that fills your lungs, the iron that carries oxygen through your blood. All of these elements were created in the nuclear furnaces of stars that lived and died before our sun was born. When those ancient stars exploded as supernovae, they scattered their elemental treasures across space. Eventually, some of those atoms found their way into a collapsing cloud of gas and dust that became our solar system. They became the Earth. They became you. This is not poetry. It is chemistry. The same nuclear reactions that light IC 1101's 100 trillion stars also created the matter from which you are made. There is a direct physical connection between you and those distant fires. In a very real sense, when you think about IC 1101, You are star stuff contemplating more star stuff. You are the universe becoming aware of itself. Carl Sagan expressed this idea beautifully when he said that we are a way for the cosmos to know itself. Through human consciousness, matter that was once scattered across space, matter that burned in the hearts of ancient stars, matter that drifted through the interstellar medium for billions of years, has come together in a configuration that can think, wonder, and ask questions. When you look at IC 1101 and feel a sense of awe, that awe is the universe experiencing wonder at its own existence. Wonder is often dismissed as childish, something we are supposed to outgrow as we become serious adults with serious concerns. But wonder is essential. It opens us to experiences beyond the everyday. It reminds us that there is more to existence than our immediate problems and pleasures. It connects us to something larger than ourselves. IC 1101 is an occasion for wonder, if anything is. 100 trillion stars, millions of light years across, a black hole of incomprehensible mass, billions of years of cosmic history, numbers so large they strain comprehension, distances so vast they defeat imagination. If you can contemplate these things without feeling a sense of awe, I do not know what would move you. But wonder does not require full understanding. You can feel wonder at IC 1101 even if you do not grasp all the science behind it. The sense of vastness, the confrontation with scales beyond human experience, the realization of how much exists beyond our small world. These are available to anyone who takes the time to really think about what we have discussed. Science enhances wonder by revealing specifics. But wonder itself is a fundamental human response to the immensity of existence. The universe is generous with its marvels. IC 1101 is just one galaxy among an estimated 2 trillion in the observable universe. Each of those galaxies has its own story, its own history of formation and growth, its own stars with their own planets. We have barely scratched the surface of cosmic discovery. The James Webb Space Telescope is revealing galaxies in the early universe that challenge our understanding. Gravitational wave observatories are detecting the collisions of black holes across cosmic time. Dark matter and dark energy remain mysterious forces that shape the cosmos in ways we do not fully comprehend. There are more wonders waiting to be discovered than have ever been found. Every answer reveals new questions. Every solved mystery opens doors to deeper mysteries. The universe is not running out of surprises. And yet, for all the vastness out there, for all the trillions of galaxies and the quintillions of stars, there is something special about being here, on Earth, in this particular corner of one particular galaxy, at this particular moment in cosmic history. We exist. We are aware. We can ask the questions and seek the answers. The entire history of the universe, from the Big Bang through the formation of stars and galaxies, through billions of years of cosmic evolution, has led to this moment when conscious minds can look out at the cosmos and wonder what it all means. IC 1101 is bigger than imagination. It stretches across distances that no human will ever cross. It contains more stars than you could count in 1,000,000 lifetimes. It holds more history than all of human civilization multiplied by billions. And yet, despite all that vastness, the fact that you can imagine it at all, the fact that you can hold in your mind a picture of 100 trillion stars spread across millions of light years, the fact that you can wonder about its past and future, that is perhaps the most amazing thing of all. The biggest galaxy we have ever discovered is out there right now, shining with the light of countless suns, growing slowly as it absorbs more material, presiding over its cluster like a cosmic emperor. It has been there for billions of years. It will remain there for billions more. And for a brief moment in the history of the cosmos, creatures made of star stuff on a small blue planet have looked up, noticed it, and understood something of what they were seeing. That connection, that thread of understanding stretching across a billion light years, is a triumph of human curiosity and ingenuity. It represents everything that is best about our species: our willingness to ask questions, our patience to seek answers, our ability to cooperate across generations and borders in the pursuit of knowledge. The fact that we can know anything at all about IC 1101 is a testament to what humanity can achieve when we turn our attention to the cosmos. Science gives us tools to understand, but wonder gives us reasons to care. The numbers that describe IC 1101, the distance in light years, the mass in solar masses, the number of stars, these are powerful and precise. But they become meaningful only when we connect them to human experience. When we try to imagine what it would be like to stand before such immensity, when we feel the vertigo of contemplating scales so different from our everyday lives. This is why astronomy continues to fascinate people around the world. It is not just the facts, but the feelings the facts evoke. The knowledge that we are small, that the universe is vast, that wonders beyond imagination exist in the darkness between stars. This knowledge changes something in us. It provides perspective. It cultivates humility. It reminds us that our daily concerns, important as they may feel, are tiny ripples in a cosmic ocean. Keep looking up. Keep wondering. The universe has more to show us than we have yet dreamed. And somewhere out there, in the direction of Virgo, the biggest galaxy ever discovered, continues its slow, majestic journey through cosmic time. A reminder that we live in a universe of giants, a universe of wonders, a universe that rewards those who take the time to look.